Hello and welcome to this lesson video where we will continue learning about trucks and hauling operations, but now under stochastic conditions. The video covers the shown four learning objectives. As a recap, in the previous lesson we learned about the typical haul process of loading, hauling, dumping, and returning. We learned how to model this operation using the multiple activity chart, which can help in identifying the cycle times, idle times, and calculating the production rate. Finally, we learned about the concept of balancing a crew, but finding the number of trucks are required to keep the loader utilized 100% of the time. All what we learned so far is based on a very critical assumption. All time and production values are deterministic. Is this a realistic assumption? Answer is no. There will always be variations in the observed times values than the estimated values. If we estimated the truck to take 10 minutes in hauling, in reality it will sometimes haul it faster or slower due to many reasons. Construction is not a closed loop or a simple system like manufacturing, as site operations depend on multiple resources at different locations. This results in some equipment waiting idle because they are waiting for other equipment to be available. There are different styles and competencies in running the equipment and performing the tasks. Construction happens in the outdoors with many unknown obstacles. The duration randomness of the hauling activities results in a phenomena we discussed before called bunching. Let's explain this phenomenon through an example. Assume a balanced crew of a loader and 3 trucks, and the truck cycle is 4.05 minutes. This means that the best production will be achieved if the time between the trucks is kept perfectly at 1.35 minutes to have the loader 100% utilized and continuously loading trucks. However, this exact headway time cannot be maintained in reality, and it will sometimes be less or more than 1.35 minutes. This deviation will result in having a truck queue in front of the loader at some times and no trucks at some other times. Once this truck queue forms, our deterministic crew production estimation based on the loader and truck's productivity values is no longer a valid approach. Actual productivity will be lower than estimated values, as the loader and trucks will not be utilized 100%. These variations in actual operation times results in lower production than the expected values. This is the production curve as covered last lesson that shows the increase of the crew's production with the increase of the number of trucks until the crew balance point. But in reality, the realized production will mostly be lower than the theoretical production curve. This fact was investigated by a study where researchers observed the productivity of a crew and compared it to the theoretical possible productivity. The horizontal axis is for the a match factor, which is the ratio between the truck and loader productivity values, which equals 1 at the balance point. The vertical axis shows the crew productivity as a percentage of the maximum achievable value by the server resource, meaning the loader. You can see that the plotted dots of the observed values are mostly below the theoretical production curve. So we need a different approach to analyze the hauling operation if we need to account for the cycle time variability. This lesson introduces one possible approach based on the queuing theory. Queuing theory follows a similar approach to paired probabilistic scheduling, but modeling the cycle production durations as random variables that follow a probability distribution like Poisson or exponential. In deterministic analysis, we are 100% certain about our statement that a whole trip will take 3.5 minutes. But with stochastic modeling, we are dealing with a probability level when relating the duration to a specific value. Let's agree on some notations and relations related to the application of queuing theory in whole operation design. Variable n is the number of the trucks in the whole crew or fleet. Pt is the probability that at least one truck will be available to be filled by the loader. Po is the complement of Pt, which to refer to the probability of having no truck at all for loading at any specific time. Variable A is the average arrival rate as the inverse of the truck transit time. Variable I is the loading rate as units per hour, which is the inverse of the loading time of the shovel or the loader. Finally, factor R is the ratio between the arrival and loading rates and equals A over L. From the previous lesson, we learned that the loading time is calculated by dividing the truck capacity over the loader production, so we can end up with the shown elaborated version of the equation for the R variable. There are three steps for calculating the production rate of a specific whole crew composition using the queuing theory. First, you will calculate PO using the shown formula that's dependent on the number of trucks in the crew and the factor R. Second, you calculate PT as the complement of PO. Finally, the crew production will equal the loader theoretical production multiplied by the truck loading readiness probability PT. There is another quicker way to calculate PT to avoid using the ugly formula of PO. We can use the PT table, which is organized by the N values in the column header and the R values in the rows headers. As shown as such, for each pair of N and R values, you can easily identify the PT probability value in decimal form. For example, in crew of 6 trucks, an R of 0.05, this crew will have a probability of 28.2% to have a truck ready to be loaded at any point of time. That was quick. Let's see an example of the queuing theory application. In this example, we are given the loading rate, truck capacity, truck transit time, and the number of trucks. We need to calculate the PT value. We will solve this example using the formula approach. First, we calculate the R factor to be 0.1. Second, we calculate the PO value as shown, and we end up with 56.4% probability that we will not have any truck available for loading at any point of time. That translates of having PT equals 43.6%. As another solution approach, we can use the PT table. We identify the column and row corresponding to 5 trucks and R equal to 0.1. This will give us right away that PT equals 43.6%, which is the same value we got from the formula-based approach, but much faster. Here's the process to design a whole crew based on stochastic settings. First, calculate R for the hauling operation. Second, calculate roughly the crew balance point as the inverse of factor R. This derivation here shows why the balance point equals the inverse of R. Next, we account for time variability by considering the crews around the balance point with 2 trucks more or less. For each crew size now around the balance point, we will need to calculate PT, the production rate, crew hourly cost, and unit cost. Finally, select the crew composition that provides the least unit cost. That's it for this lesson, where you learned about the impact of time variability on whole operation, production estimates, and the application of the queuing theory to account for such impact. What you learned here can be applied in other similar construction operations like earthwork scraper operations. See you in another lesson.